EDX Corpio, Calculus, Volumes of Revolution, the Introduction. The area under a curve. We can find the area under a curve by splitting the required area up into equal width strips. So here we've cut the area up into 5 strips, and the area is the sum of these individual areas. If we make the width of the strip, which we call delta x, in this case delta x was 0.4. If we make delta x even smaller, so here we've gone for delta x is 0.1, you can see that when we find the sum of the areas of the strips, we get a much better approximation for the area underneath the curve. So integration is a limiting process where the sum of rectangle areas is used as an approximation to the area under the curve. As the rectangle width delta x becomes smaller, and hence more of them are needed, the approximation for the area becomes more and more accurate. So if we look at this diagram in a little bit more detail, so if we look at this strip where the coordinates at that point is x, f of x, and this has a width of delta x, then the area of that strip, so that one strip on its own, the rectangle is the height f of x times the width delta x. And if we had lots of these strips, so if we looked at lots and lots of these strips lined up one after another, we get the area underneath the curve is approximately the sum of all these strips, f of x delta x's, starting at the beginning of the area, which is usually A, and the end of the area, which is usually denoted by B. So A, the area, is approximately the sum of f of x delta x from A to B. What we do now is we let delta x get smaller and smaller. So we let delta x tend to 0, so we get more and more of these strips, and the area becomes equal to the limit as delta x gets smaller of the sum of f of x delta x's starting at x is A and finishing at x equals B. Once delta x gets to 0, then the area is the integral of f of x dx from x equals A to x equals B. And that is what we can use to find the area between a curve and the x-axis. So there's the clear explanation of how we find the area underneath a curve. We can also now look at volumes of revolution. The same idea can be used to find the volume of a solid formed when a curve is rotated about one of the axes. So here we've taken a simple curve and rotated it about the x-axis to create a volume. And you can see that the approximate volume generated is these 5 cylinders. But when we make, so this is delta x here, so there's delta x, but when we make delta x much smaller, so delta x is much closer to 0, you can see the volume is more accurate. And we're going to look at this in a little bit of detail in this piece of software. So here I've entered the curve y equals x squared, and I've started off by looking at the approximate area from x equals 1 to x equals 3 using 5 strips. Now if I click on that area and ask it to find a volume, so it's now going to spin that area around the x-axis. And you can see it's generated an approximate volume generated by rotating the curve around the x-axis. But here delta x is quite big. Okay, so here we've got 5 strips, so here delta x is 0.4. So if I click on this volume and edit the object and edit the area, and instead of having 5 strips we go for 20 strips, you can see that we get a much better idea of the volume generated. And if we let delta x tend to 0, we will end up with an exact volume generated by rotating this curve about the x-axis. So this idea will be investigated in the next 2 videos. So in the next session we're going to be rotating the curve about the x-axis.